Great. Well, first of all, I want to thank Fred and Aaron and the Walker family for inviting us here today, getting us here, organizing this great event for all of us. Let's give them a big round of applause, please. And I want to thank all of you for coming to this event. I know it's Saturday morning. There's a football game on. Coincidentally, we were just yesterday at the University of at Ohio State University, which I hear. Yesterday we were there because we wanted to save the best for last. Awesome. Well, thank you for being here. Raise your hand if you were just here for the donuts. The donuts. All right, good. All right, we have a few graduate students in the audience here today. Well, great. My name is Jorge Cham. I am a cartoonist, and I'm here with Professor Daniel Whiteson. And together we wrote this book called We Have No Idea. And so today I'll just spend a couple of minutes just talking to you about how we got together to write this book. And then Daniel's going to come up and talk to you about the ideas inside of We Have No Idea. Now, I am a cartoonist. I draw comics for a living. And to me, cartooning is about taking a blank page and filling it and drawing out an idea. And so the idea we want to draw out for all of you here today is this idea that there are still big gaps in our knowledge of the universe. Now, I am a cartoonist, but I also happen to have a PhD in robotics. Yeah. I don't know why that's funny, but no, I'm just kidding. I guess you might be wondering, what does being a cartoonist have to do with being a roboticist, having a PhD in robotics? Well, I can tell you that my parents are also very worried about that whole career plan. But I have a PhD in robotics, and in fact, my thesis work, my research focused on making small robots that could run and walk. And specifically, I was trying to make robots that could run like cockroaches. Yeah. Sweet. So here's a quick movie of what these robots look like. All right, cool, awesome. Not that many people applaud my PhD research. But yeah, that was my thesis, and I'd like to show this movie. I feel like it's very important in every presentation I give because I feel like this video really kind of captures what getting a PhD feels like. You might know somebody who's been through it, but it feels like you're running frantically the whole time, but you're not getting anywhere. Meanwhile, there's a more intelligent being stamping you down. But I like to show this movie also because it's kind of the only way that anyone will look at my research. Gotcha. Because despite the fact that I was doing this PhD, I think a little bit more popular has been what I was doing I think a little more popular has been what I did when I should have been doing research. Instead of doing research, which was to draw comics, in particular this comic strip called PhD Comics. Oh, all right, thanks. Cool. Yeah, these were just a comic strip that I started drawing while I was in graduate school. And what happened was that I saw this advertisement in the newspaper at some point calling for comics from students. And so I thought, hey, somebody should draw a comic about graduate students and express some of the things that graduate students go through, like, for example, meeting with professors. begging them to take Jan into their labs. I started drawing these comics, and the comics were also about being a teaching assistant. You know, having to teach those annoying undergraduates. I apologize if there are any in the room here today. I'm sure you're cool. Yeah, the comics were also about learning graduate student etiquette. Never ask a graduate student how their research is going. That's just rude. Yeah, and so I started drawing these comics, and then at some point I just kind of took my procrastination to the next level. And I started, to the next level. And I just started posting these on the internet. And so I think what happened is most things happen on the internet. Somebody read it there and liked it, and they told their friends in other universities, and they told their other friends in other universities, and those people told their friends in other places. And so slowly over the years, kind of like a virus, or a Tupperware party. These comics kind of went out into the world to the point where these days about 5 to 6 million people a year come visit the PhD Comics website, which sounds like an enormously small number. If you actually think about the fact that there are 7 billion people on this planet. But it just so happened that one of these 1 in 1,000 people that read these comics was this professor at the University of California at Irvine. And so what happened was that one day, this professor decided to email me. And so one morning, I just checked my email, and I get this message from this professor saying, Jorge, I've seen your comics on the internet, and I think they're pretty good at explaining stuff. So I would like to pay you, I would like to commission you to draw some comics about the Higgs boson. And so I thought, what? What? You want to pay me? What? What is that? I don't understand. I just put things on the internet for free. But I said, yeah, that sounds awesome. And what happened was that Daniel, this was a couple of years ago, before they discovered the famous Higgs boson, and there was a lot of articles, a lot of buzz in the media about it. But Daniel had seen all of these articles, and he didn't think that people were doing a very good job of explaining what the Higgs boson was and why they were looking for it and how they were looking for it. And so he decided to take that initiative and contact a cartoonist to create something that communicated that to the public. And so I thought, hey, how much are you paying me? I said, yeah, that sounds really cool. So I went down and I had this long conversation with Daniel about the Higgs boson. About 4 hours we talked there at the cafeteria. And instead of taking notes, I recorded our conversation. And so what happened was that when I went home to draw this comic, I decided to experiment a little bit. And so I took that recording, I edited it, and I recorded myself drawing the comics. And then I kind of matched the two to create kind of a comic video mixture piece that explained what the Higgs boson was. And so I'll play for you just a couple of minutes of this video and comic, just to give you a sense of how our collaboration started. So here's a little bit of it.
So one of the things people predict is the Higgs boson.
The idea is that the Higgs boson is the particle that is responsible for giving mass to the other particles. So you think of things that have mass means it has stuff to it. It's not actually stuff. Earlier I was saying an electron has mass, but has no volume. How can that be? Mm-hmm. Turns out mass is probably just a characteristic of a particle the way like charge is. Like some particles have charge, like electrons. Some particles don't. It's just a different kind of charge. So you can think of mass as sort of gravitational charge. And when two things both have mass, they attract each other. Right. Interestingly, you can't have negative mass or repulsive gravity. So the collision happens. It lasts for like 10 to the negative 23 seconds, and you get one measurement, right? So if you say, well, I'm going to plot the mass, the total energy of this guy. I'm going to add this guy and this guy together and add the total energy. This axis here is number of collisions. You do an individual experiment, you get one measurement, right? Here. You do another one, you get another measurement. You do another one. Eventually you build up your data, right? And the data looks like this, for example. And then you have two theories, right, that predict the data. One says, well, I'm going to predict there's no Higgs boson, so the data should fall along this line. And the other is I'm going to predict that plus a Higgs boson. And the problem is the difference between these two theories is very small.
And so it's very hard to distinguish these two with our data because the predicted effect is tiny, right? If the predicted effect were huge, it'd be very easy to tell the difference between with Higgs boson or not with Higgs boson. But the predicted effect is tiny, and so it's really hard to see. What you need is a huge amount of data. You need to take a bajillion collisions before you can see the difference. That's why we run this thing 40 million times a second, all day, all year, to get a lot of collisions to tell small differences between theories. It's like when you take a picture of the sky. You just take a picture, you get a little bit of light. The longer you leave your telescope looking at the sky, the more you can see farther away things.
Cool, yeah. That was the video that we first made together, and so we decided to take a little bit of a risk, and we just put it out there on the internet, on YouTube, and on the PhD Comics website, and people liked it. A few hundred thousand people saw this video, and they liked it. But then what happened was that they actually discovered the Higgs boson. And then that's when the video really exploded. Millions and millions of people watched this video, and they read the comics, and websites like the New York Times or CBS News, they were pointing to this video as the clearest and most easy to understand explanation of what the Higgs boson was. And so I think that's pretty cool that the video and the comic, the thing that people were pointing to as the clearest and most easiest to understand, it didn't come from a reporter at the New York Times, it didn't come from a media person at CBS News, it actually came from one of the scientists who worked on the project, who decided to take that initiative and create something that communicated that to the public. So if we have any scientists here in the room here today, I would highly encourage you to also take that initiative and to really make that effort to communicate what you do to the public. Yeah, so that was our first collaboration together. And we've worked on a couple of other things, but our latest project is this book called We Have No Idea. And so to talk to you about We Have No Idea is Professor Daniel Whiteson.
Good morning, everyone. Wonderful to be here. It's a real pleasure. Thank you, Aaron and Fred and everybody for organizing. It's also been a real pleasure to work on this project with Jorge. It's a fantastic creative collaboration. For those of you who don't know, Jorge is not just some cartoonist online. In academic circles, Jorge is a verifiable rock star. Okay, he's a celebrity. I mean, I go around the world, I visit places, in physics labs, biology labs, everywhere you go, you find one of his cartoons up on the wall. Because not only does he make us laugh, but he's captured the suffering of research and the frustration of that experience. So he really is a celebrity. So when I first had the idea, maybe we can explain physics using cartoons or comics, unfortunately I don't have much artistic talent myself, so I thought, who can I get to draw these cartoons? So my wife, who's also an academic, she's a huge fan of Jorge, she said, why don't you email Jorge Cham and get him to do it? And I thought, yeah, right. And then afterwards I'll email Brad Pitt, and maybe we can do a movie together, right? But turns out Brad doesn't answer phone calls, but Jorge does, so yeah, so here I got to do this fantastic project with Jorge. Okay, so we're here to talk about our book. The book is called We Have No Idea. There are a lot of popular science books being written these days, and most of them are about all the things that science has figured out, which is awesome, because science has figured out a lot of cool stuff, and we should be talking about it. But for me, science is more about learning things than about knowing things. So our book is not about what we know, it's about what we don't know. It's about all of our cosmic ignorance and all the things we have to look forward to learning about, right? So if you hear a talk by an author about a science book, you expect to hear from an authority on the topic, right? So if our book is about not knowing things, you might be wondering, well, what's my expertise, right? Am I a special expert in not having ideas or not answering questions or something? So it's not that I want to express any particular personal expertise in ignorance, it's just that I feel a really strong passion for all the questions we don't have answers to. Because for me, science is about exploration. It's about facing our ignorance and exploring it in order to get those answers. And it really comes from when I was a kid, and I was learning about the Age of Explorers, and I thought that sounded like a lot of fun. I mean, these guys got to jump on a ship and sail across an ocean, and then they could walk on a new beach that nobody had ever stepped on before, and they could taste a new fruit that no human had ever eaten, right? They got to be at the forefront of human knowledge, and to me that was really exciting, because they were exploring the universe, and they were figuring things out for the first time. I mean, imagine what it was like to be the first person to ever see the Grand Canyon, right? wow, what an amazing experience. Or the first person to ever eat chocolate, right? Somebody got to do that for the first time. Or the first person to ever eat chocolate while looking at the Grand Canyon, right? Like, these are all firsts in human history. They all count. And I wanted one for myself. But as you learn about the Age of Explorers, you also sort of feel like maybe it's over, right? Like, there aren't any more continents to discover. There aren't any more islands to land on and name after yourself, right? Most of the fruits have been tasted, probably. So that's a little bit of a come down. And then the more you look around at the world, the more you marvel at our technological achievements, right? I mean, we have airplanes that can fly across oceans. You can download all of human knowledge onto a tiny device you fit into your pocket, right? Clearly, we live in an age of wonders, right? And you might be forgiven for thinking science has it mostly figured out. You know, we've mapped out the world, we've mastered technology, and physics has mostly figured everything out. It's just a couple of details left, right? Which means Brad Pitt has no excuse not to call me, right? Wherever he is, he could pick up the phone. So you might feel like science isn't mostly figured out, right? So the point of my book, of our book and the presentation today, is to make exactly the opposite point. I feel like we're at the beginning of a new age of discovery, a new era of exploration, where we're going to answer basic questions about the universe that we're still ignorant about, right? We are at primitive stages when it comes to the fraction of the universe that we have understood. And so that's the point of today's book, is to encourage you to think about all the things we don't understand and that we get to figure out, right? All right, Jorge, that's enough. Thank you. So what kind of exploration are we talking about? Because it's not the case that there's an island out there waiting for you to discover it, right? That really is done. I'm talking about really big questions about the universe, big, fat, juicy questions, right? The kind of question you don't need to have a science degree to understand why the question is important and to want to know the answer, right? The kind of question where if you knew the answer, it would change the way you felt about life, about the human experience, right? The entire human context, right? Really basic questions. So what am I talking about? Well, if you walk down the street in a place like in Ann Arbor where everybody's smart and good looking, and you ask them questions like, what's the most important thing in life? Or what question would you want to know the answer to? They might say things like this, like, well, why are we here, right? That's a classic question people want to know the answer to. Or what happens after we die? I would certainly like to know the answer to that question. And if you knew the answer, it might change the way you live your life, right? All right, we can all agree about that. There are other questions in this category, like this one. What is it like to be a bat? And you might think, well, certainly he's joking about that, right? Well, this is actually the title of the most widely cited philosophy paper of all time, okay? Which means in philosophy departments across the country, people talk about this. People argue about this. They've been talking about it for decades, and they will continue. Okay? And that's the problem, is that it doesn't matter how many banana peels these guys smoke, they're never going to get an answer to this question, right? They'll talk about it forever. And that's the problem with this whole category of questions, is that, yeah, they're interesting, they're important, I want to know the answer, but we might not ever figure it out, right? And reasonable people can disagree forever about the answer to these questions. To me, the really exciting thing is that in this category of questions, there are other questions, but these are science questions, but they're at the same level of importance, the same gut level, like, wow, I'd like to know the answer. But these questions have answers, right? Questions like, what is everything made out of? How did the universe begin? Think about that one, right? The universe has one true history. It started in one way and in no other way. People have been wondering about it forever, right? How did all of this come to be? Imagine if you knew the answer to that question, right? That would change the way you felt about life and what you should do with yourself, and should you even study for that English test, right? And the interesting thing to me is that there is an answer, and the answer is out there. And if we piece together, clues from the Big Bang or whatever, or experimentally are very clever, we can learn the answer. Someday, somebody will know the answer to that question. And they will look back at us and they will say, what was it like to live in such ignorance, right? We are in primitive days. We are basically cavemen when it comes to our knowledge of the universe. And to me, it's exciting because these questions do have answers. So I focus my professional career on this one. What is the universe made out of? To me, it's a pretty basic question. I'd like to know the answer, right? What am I made out of? What is this table made of? What is the whole organizing principle behind this whole thing, right? It's a pretty simple question to want to know the answer to. It's shocking that we don't know the answer, right? I also think it's probably a pretty ancient question. I think people have been asking this question since people have been asking questions, right? All you need to be inspired to ask this question is take two rocks, bang them together, and get smaller rocks. And then you take those rocks, bang them together, and you just keep going, right? And eventually you wonder, can I go on forever and get infinitely small rocks, right? Or eventually does it stop being something else to turn into like not rock? Is there a minimum rock size, right? So I like to think of this as like the particle physics superhero creation myth, right? This is when it was all born. Yeah, we all wear capes in the lab all day long. I remember asking myself this question, like how small can a rock get as a child? And so maybe it's not a surprise I became a particle physicist. But imagine this was you. You are a caveman or cavewoman physicist, and you are asking this question for the first time. What is the universe made out of, okay? You get the first crack at this big question, right? How do you approach such a hard question? How do you tackle such a cosmically sized question? Well, in science, when we have to answer a hard question, what we do is we just do the dumbest thing first, right? What's the simplest way to approach this question? If that doesn't work, then we try something a little smarter and then a little smarter until eventually we get a satisfying answer. Okay, so what's the simplest approach to answering the question, what is the universe made out of? Well, you might try just by making a list. What's in the universe, right? Just look around you and first start cataloging, like, what's the stuff here, right? I'm in the universe, you're in the universe. It's caveman times, right? So there's a lot of rocks in the universe still. That's a basic element of the universe, right? Even back then, Brad Pitt didn't answer my phone calls. But there's a lot of problems with this approach, right? First of all, there's a lot of rocks in the universe, right? He doesn't answer my phone calls either. There's a lot of rocks in the universe, so if you make a list, it's going to be really, really long, right? The other problem is that there's more than just rocks in the universe, right? And so as you start making your list, you're going to be overwhelmed with the incredible complexity. If you want to answer this question, what is the universe made out of, you have to explain all the different kind of stuff you see, right? Not just rocks, but iPhones and blueberries and ice cream and mushrooms, right? You have to explain all this crazy stuff. And the more you look, the more you're overwhelmed by the complexity, right? Puppies and bicycles and strangely muscular guys become governor of California, right? It's an incredible world we live in, right? And that's one of the things that makes it a nice place to live, right? It would be boring. It would be boring if it was not just rocks, right? You don't want me to take my shirt off. So if you're going to answer this question, you have to explain all this incredible complexity. And it makes you wonder, what kind of answer do we want, right? Is a list really the right answer? I mean, imagine you had a genie, or you could speak to God, or you believe in oracles or whatever, and you could ask one question and get an answer. And you asked, what is the universe made out of? And you got a list of everything in the universe, right? That's not a satisfying answer, right? It doesn't give you any insight. You don't go, aha, I get it now, right? It's like if you're a teenager and your parents ask you, where are you going? And you say, out, right? All right, you answered the question, but you didn't really answer the question, right? So what kind of answer are we looking for to the question, what is the universe made out of? We're looking for a simplification, right? We want a reductionist answer. We're not botanists. We don't just enumerate knowledge and say we're done, right? We simplify. We want to reveal a deeper layer of understanding. We want to peel back a layer of the universe and say, aha, all of this complexity can be explained using only a few simple objects, right? So how do we get there? Well, we make a list of everything we see, and then we organize it, right? We categorize it into groups, and we look for patterns. And we say, oh, the living stuff is all similar to itself, and the rocks over here are all similar to themselves. And, reasonable people disagree about whether Arnold belongs in the living thing category or maybe in the rock category, right? But everything belongs in a category somewhere, and you look for patterns, and then you ask yourself, why are there these patterns? What do these patterns mean? Because those patterns are clues to help you understand what's going on at a lower level, right? And so fast forward this process a few hundred years or a few thousand years, if you believe the Greeks get any credit. Personally, I don't. And you can explain everything in our world, everything in our experience, in terms of just a few elements of the periodic table, right? 100 basic building blocks describe anything any person has ever eaten or sat on or interacted with throughout all of human history. All of that stuff can be explained in terms of just 100 basic building blocks. Wow. Now, you guys might be thinking, this guy is supposed to be a particle physicist. He's telling us basic high school chemistry. What's going on, right? It's true, this is high school chemistry. It's also, in my opinion, one of the most underrated intellectual achievements in human history. Why? Because you've gone from almost infinite complexity down to 100 basic building blocks, right? If your goal is to explain this almost infinite complexity in terms of one or two particles, you're most of the way there already. The rest is really just details, right? That's the hardest step, infinity down to a finite number. It blows my mind, like, why is that even possible? Why does the universe seem to be organized in this way that incredible complexity can be explained at a lower level in terms of a small set of building blocks, right? It reminds me of something. It's almost like the universe is just a big demonstration by the Lego company, right? I mean, this is the Lego philosophy, right? A few basic objects, and you can make anything, right? You can make dinosaurs, you can make pirates, you can make dinosaur pirates, whatever your mind imagines, you can make using Legos, right? Why is it this way? We don't know. We have no idea why the universe seems to be organized according to the Lego principle, but it is. And it could have been different, right? Imagine another universe where everything wasn't made out of a few basic building blocks, right? Imagine a universe where everything was made out of its own little particle, right? Cats made out of their own little cat particles, and that explains why they're so weird, right? Physicists made out of little physicistinos or something, right? It could have been that everything was made out of its own kind of particle. We don't live in that universe, fortunately, which makes particle physics more satisfying as an intellectual adventure, but we don't know why. All right, so here we are at the periodic table. And again, we don't just list our knowledge and say, okay, we're done, here's the answer to the question, because there are other layers. We want to get to those layers. The way we get to those layers is we organize the knowledge and we look for patterns, right? So of course there are patterns in the periodic table, right? It's periodic, after all. And I'm not a chemist, but you know, these guys over here are really active, and those guys over there are very inactive, et cetera, et cetera. And you have to wonder, why are there these patterns? Why are there these features? What is going on in the periodic table? Now, 100 years ago, or 150 years ago, they didn't know, and they looked at that and they thought, what is going on, right? Now, of course, we know that all the structures of the periodic table are just clues that point you to what's going on inside at the lower level, right? They're not just there for Jorge to play Tetris with, right, when he gets bored. There are patterns, and everything that's in the periodic table is an emergent phenomena. That complexity comes from a simpler structure, and that's just the structure of the atom. Right? The protons and neutrons in the nucleus and the electrons whizzing around it, all of those things, the way they interact and the way they structure and the way electrons fill their orbitals, et cetera, all of that explains everything you see in the periodic table. The same way the periodic table and all those elements explain everything you see in the universe, right? So there's all these layers, and at each layer you see patterns, you ask yourself questions, those questions are clues to lead you to a deeper, deeper level, right? Eventually, we will discover the basic hula hoops of the universe. Okay, but the atom is not the most fundamental building block of the universe, right? In fact, nothing that you know, nothing you've seen or tasted or interacted with, nothing that you hold in your mind is a good model for what is the most fundamental building block of the universe. Because the universe works in a weird way deep down, right? It's not made out of atoms, it's not made out of llamas, it's not made out of tornadoes, right? It's not made out of llama tornadoes, right? Though we're pitching that as a series for Sci-Fi Channel next year. If they do shark tornadoes, they should do llama tornadoes, right? So none of these are the basic building blocks of the universe, right? So let's dig a little deeper. What is it inside the atom? Well, you have the neutrons and the protons in the nucleus surrounded by the electrons. The neutrons and the protons are themselves built out of smaller particles. Here you have the up quarks and the down quarks. Now, to me, this is incredible because it means with just up quarks, down quarks, and electrons, you can build any atom. Anything in the periodic table is made out of just those three particles. And anything in the periodic table, you can make anything, right? So if you ask a physicist, for example, to write a cookbook, they could say, well, there's only 3 ingredients, right? Up quarks, down quarks, and electrons, right? And the recipe for everything is just combine and mix, right? That's the reductionist cookbook of the universe. And so it's incredible progress. And you might think, well, if our goal is to explain what the universe is made out of, we went from infinite complexity to 100 elements of the periodic table, down to just 3 particles, right? Next week, these guys will get down to 1 particle, right? And we'll have the 1 particle that explains it all. And so we have made great progress, but the answer is not so simple. And the reason is that these aren't the only particles that we found. So the up quark and the down quark are quarks, but they're examples of other quarks. They're examples of a category of particle we call quarks, right? There's also the charm quark, the strange quark, the top quark, the bottom quark, right? Not responsible for the names of these particles, okay? And the electron is just an example of a particle called a lepton, and there's 5 other leptons as well. So here we are, we have these 12 particles, right? We're curious about them, but remember, we don't just list our knowledge and say, here's the answer, we're done, right? We organize this knowledge, and we ask questions about it. Yeah? Questions like, who invited all these other particles, right? So now we have a new periodic table, but it's a periodic table of the fundamental particles. Why do we make the periodic table? In order to look for patterns, because we hope those patterns will generate questions and clues to help us reveal one more layer of reality underneath all of this, right? And so let's take a look at this periodic table. We have the up quark, the down quark, and the electron. That's what you need to make, chocolate cakes and hamsters and stars, etc. In this column, we also put the neutrino, which is a really weird, mysterious little particle. Not weird because it's rare. Actually, it's very, very common. There's 100 billion, with a B, 100 billion neutrinos passing through my fingernail every second, right? And your fingernail, right? So why are we not beaten down by all this cosmic neutrino radiation, right? Or instantly getting cancer or something? The reason is that the neutrinos pass right through us without even noticing. And we don't notice them, and they don't notice us. A neutrino can pass through a huge amount of lead or rock without even noticing. How much? A light year of lead. Okay? That's a huge amount of lead, and it doesn't even notice. It shrugs it off, right? So neutrinos, they're everywhere. They're all around us, but we can't interact with them. So it's like this mysterious other universe that's right here with us. It's a clue. There's a lot of things going on in the universe that we don't see and can't observe directly. Okay, so we have those 4 particles. The fascinating thing is, of these 12, the other 8 seem to be just copies of these first 4, right? So for example, the charm quark is a copy of the up quark. It has the same charge, the same spin, all the same interactions. It's just heavier. It's like the up quark has a secret heavy fat cousin or something, right? Why does it exist? We don't know. And then there's the top quark, which also has all the same properties as the up quark, but it's even more massive. It's incredibly massive, right? It's like that secret fat cousin nobody talks about because they can't even leave the house, right? Yeah. So, and the other particles follow the same pattern, right? The strange and the bottom quarks are just copies of the down quark, but heavier. Why? We don't know. The muon and the tau follow the same pattern. They're copies of the electron, but heavier. And even these 3 particles at the bottom, the neutrinos, there are 3 of them. We're not exactly clear yet on the patterns of the masses. We still have to figure that out. But there are clearly patterns here, right? And these patterns are clues, and they're telling us there's something going on, right? There's some way to explain this at a lower level. We don't know what the answer is, right? We still have no idea. But these are definitely clues, right? And so all of these patterns lead us to ask questions. Questions like, why do we have all these particles? What are they for? You need the up-down electron to explain most of matter. Why do we have the other ones? Why are there 12 particles? Or are there, in fact, only 12 particles? There could be more. Nothing in theoretical physics prevents us from having 1,200 particles or 12 million particles, right? Is this the entire ice cube, or is this just the tip of the iceberg? We have no idea, right? Why are some particles heavy and some of them light? The Higgs boson, we know, gives the particles mass, but we don't know why it gives some of them a lot of mass and some of them almost no mass. To me, one of the deepest questions is why there are 2 copies of each particle, right? And to me, numbers are really interesting in physics. Like when you see a number in physics, you have to ask, what does that number mean? So one of the goals of physics is to get all of physics explained in a single equation that's so simple it fits on a t-shirt, right? Okay, the t-shirt theory of physics. Imagine you had that equation and you looked at it and there was a number in it, right? Like the number 7. That would mean that there's something like deeply 7-ish about the universe, right? It means, oh, 7's an important number. Okay, so you go and ask mathematicians or theoretical physicists, you say, what numbers do you expect to see in that equation, right? What would make sense to you? And they say, okay, 1 or pi, e, they like that, right? Maybe 2 sometimes. Nobody says 3, right? We have these 3 columns of particles, but nobody says 3 is a deep number in the universe unless, they're Catholic or something. And maybe the Catholics are right? Maybe there's a holy trinity in the particles. So to me, this is like a really interesting clue. Something is going on here. It's the kind of clue that in 100 years, physics undergraduates will know the answer to, and they'll look back and they'll say, God, it was so obvious. How could they not have figured it out? If I was a physicist in 2017, I would have figured it out. I would have won the Nobel Prize. Man, they had it so easy. But here we are at the forefront of human ignorance, looking forward and not knowing what the answer is. We know it's a clue. It's screaming clue, 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 clue at us. We just don't really know what it means yet, right? Another really interesting thing about numbers is this question of the electric charges. So the quarks have these really funny electric charges, right? 1/3, 2/3. The convenient thing is that the quark charges add up when you make them into a proton into +1, which perfectly balances the electron charge of -1, right? It's important that it balances because otherwise you couldn't get a neutral atom, and without that you can't get chemistry and biology and silly physics books and all sorts of fun stuff. And so you might ask, well, why does that happen? Well, in our current theory of physics, the charge of the quarks and the charge of the leptons are two independent numbers. So you're at the control panel of the universe, right, dialing these things up and down. You can get good theories of physics for lots of different values of these things. So according to our current theory, the fact that these two things balance exactly is a coincidence, right? A coincidence, right? And this is an exact balance. This is not like the sun and the moon in the sky are almost the same size, which means we can have eclipses. That's a cool coincidence. That's a 1% coincidence, right? This is an exact coincidence. So either it's crazy lucky, or there's some connection between the quarks and the leptons that we just haven't figured out yet. They're two sides of the same coin, or at some lower level, they're built out of the same kind of stuff, right? We just don't know what it is. It's another thing that's obviously a clue that we don't yet know how to interpret. But we don't just think about the matter particles themselves, we also think about how they talk to each other. And long before we had Jorge as the favorite cartoonist of particle physics, we had Richard Feynman, and he invented a sort of cartoony way to think about how particles talk to each other. It's called the Feynman diagram. You see some examples up there. And the matter particles are the lines, and the wiggles are how they talk to each other. And we use these cartoons to do calculations, and we can use these calculations to predict how particles talk to each other. The amazing thing is, when we do these calculations, we get the answer right. And not just like close, we get it right bang on to like 10 decimal places. That's not something that happens by chance, right? That's like, if that was to happen by chance, it's like hitting a golf ball in New York and getting a hole-in-one in China, right? That's about as likely it is to happen by chance. So there's something deeply correct about the theory. It's really describing what's happening. Otherwise, it wouldn't get it so accurate. But remember, our goal is not just to get an accurate theory of physics. We want a simple theory of physics. We want something that fits onto a T-shirt, right? So we measure our theory also by its simplicity. So here's the current equation for the standard model of particle physics, right? There's actually the Hermitian conjugate terms didn't fit on the page. And you might ask, like, can I get that on a T-shirt, right? Can I get 1-point font or something to fit that onto a T-shirt? You'd have to be like extra, extra large size, right? Anyway, so we certainly have a ways to go before we figure that out. But if you're going to answer the question, what is the universe made out of? The biggest problem is not all these remaining questions about how the particles interact, though those are deep, deep questions. The biggest problem is that it turns out all the stuff we've been focusing on, me and you and hamsters and rocks and ice cream, all that stuff is not representative of what's out there in the universe. It's in fact a tiny little slice of what's in the universe. This stuff, me, you, stars, dust, galaxies, all that stuff is a little slice. It's less than 5% of the stuff in the universe, okay? So you've been asking this question, what's the universe made out of? And we've just been focusing on a little tiny piece, right? The rest of the universe is something totally different, something we're only now beginning to understand that we don't understand. And we've measured this fraction very, very precisely in lots of different ways, so we're very confident. It's an era of precision ignorance, where we've measured very, very, very well exactly how little we know about the universe, right? And to me, that's exciting, right? I don't say that to denigrate science at all. I say that like, look at all this unexplored territory, right? What if somebody told you, oh, we've only explored 5% of the land on Earth? I think, awesome, let's go check it out, right? That's exciting. That's opportunity. That means that me or you or your children, somebody will figure this stuff out. There's a lot of juice left in the apple of physics, okay? So how is it possible that we could know, that we don't know that much about the universe? What is this stuff? Well, one clue we got was by looking at how galaxies spin. So you look at galaxies, and you can think of galaxies as like massive cosmic merry-go-rounds, okay, with a bunch of ping pong balls on them. But what happens if you spin a merry-go-round with ping pong balls on it? Ping pong balls are going to fly out everywhere, right? Unless there's something holding them in. So in the case of galaxies, that force is gravity. Gravity is keeping the stars from being thrown out into intergalactic space when the galaxies spin. Okay, so you can do something cool, is you can say, how fast are the galaxies spinning? And then you can ask, is there enough gravity in that galaxy to hold the stars in, right? So you can measure two things and check them against each other. So they did this, they went out and they measured this, and they expected it to be just a cross-check, yeah, we'll go home on a Friday night, no problem. Turns out the answer is the galaxies are spinning way too fast, right? There's not nearly enough gravity to hold the stars in these galaxies. But the stars are not getting thrown out into intergalactic space all the time, right? Something is holding them in. So they thought, well, we can't see anything else giving us this extra gravity, so there must be something else invisible that's giving us gravity. So they came up with this idea of dark matter, some new kind of invisible matter that's in these galaxies that's giving us extra gravity, right? You might think, well, that sounds really clever. It's sort of a physics trick, right? Your question is like, what could be invisibly giving us extra gravity? And you come up with a new theory and you call it, well, how about a new invisible gravity-giving thing, right? That's dark matter, right? Dark meaning invisible, matter meaning giving gravity. So it's like turn the question into a theory, right? I love that idea. All right, so they said, well, maybe this is invisible stuff inside the galaxy, right? So let's think for a moment what it means for matter to be dark. What do we mean by dark? Okay, so we have to think about how matter can interact. There's gravity, right? Anything that has mass is going to feel gravity. It's going to attract itself. Then there's electromagnetism. Anything that gives off light or reflects light feels the electromagnetic force, right? And this is one of the major forces you feel in your everyday life. When you press down on a table, right? It's the electromagnetic forces between the molecules in the table act like a mesh or like a chain link fence and prevent your finger from going through it. And then there's the weak force and the strong force that break up the nucleus and hold it together. So in the case of dark matter, we know that dark matter feels gravity, right? We invented it to solve this problem of the missing gravity inside these galaxies. We know it doesn't feel electromagnetism, or it wouldn't be dark, right? It would give off light, it would reflect light. We could be able to see it, but we can't. It doesn't feel the weak force. It doesn't feel the strong nuclear force. As far as we can tell, gravity has no interactions dark matter has no interactions other than gravity, right? There's no way to contact it. There's no way to feel it, right? It doesn't respond to any of my Facebook requests, right? It's not even on Google+, I've checked, okay? Nobody's on that thing anymore. Yeah, it doesn't tweet or anything. So it might be that there's a new kind of force that we haven't discovered yet that we can use to interact with dark matter, but as far as we can tell, so far, it only feels gravity, okay? And it's not a small part of the universe, right? 5% of the universe is me, you, gas, stars, hamsters, ice cream, etc. And in order to explain the missing gravity in these galaxies, you don't just have to add a little bit. It's not like a 1% correction or 2% correction, right? You have to add an incredible amount of stuff to these galaxies for the rotation to make sense, right? You have to multiply the amount of matter you thought was in the universe by a factor of 5, right? So normal matter is 5% of the universe. Dark matter is 27%, right? Our normal matter is not actually normal, right? We're the abnormal matter in the universe. We're the unusual bit of the universe. Dark matter is much more common, right? But it seems like a crazy theory. If somebody says, look, my experiment didn't work, so I'm going to postulate an incredible amount of invisible stuff that fills the universe and explains why my experiment didn't work, right? You might be skeptical at first. You might think, well, maybe you should check your experiment, right? So before people believed dark matter really was a thing, they had to find other ways to see it, to convince themselves it really was a thing. And one really awesome way is gravitational lensing. So dark matter is dark, it's invisible, it doesn't give off light, but it can act like a lens because it has gravity, it has mass, right? And so it can bend space. So in space, it can act like a cosmic lens. What does that mean? Well, if there's a big blob of dark matter between you and another galaxy, imagine what happens to a photon that leaves that galaxy, right? It flies off through space, and then because of the dark matter, it gets bent towards your telescope. Another photon flying off in another direction from that same galaxy also gets bent towards your telescope. So if you look in the sky in two different places, you can see the same galaxy, right? That's incredible. It means either you've been in the philosophy department smoking banana peels too long, or right, there's an invisible cosmic lens out there in the sky that's bending the light, acting like a lens in the sky. That's pretty incredible. And if you haven't ever seen that before, I encourage you later to do Google image search on gravitational lensing. You can see these pictures. They're optical pictures, and you can see distortions, and it looks really just like a lens in the sky. It's incredible. But one of the most interesting and fascinating pieces of evidence for dark matter is from a cosmic collision. So I'm a particle physicist. I like to solve problems by smashing stuff together, okay? You ask me, how does this work? I'll say, how's my toaster work? I'll say, well, let's break it apart and see what's inside, right? That's my go-to solution. But when it comes to understanding galaxies, right, it's financially not really feasible to build a galaxy collider, right? I've asked the NSF about this. They say, they don't have $10 trillion. So astrophysicists tend to have a different approach. Instead of building an experiment to see what's going on, they just look out into the universe and try to find it happening already. Because the universe, after all, is huge and full of crazy stuff, and you look long enough, you'll find anything. So they found this collision of cosmic clusters of galaxies, and each cluster has both normal matter and dark matter clumped together, right? Then they smashed together, and we were able to witness this collision. And what happened is that the normal matter smashed into itself, huge explosions, right? Transformers movie. And the dark matter passed right through the normal matter and through itself, okay? Because dark matter doesn't interact with normal matter, and it doesn't interact with itself. So it got separated from the normal matter and passed right through. We can see where it is, thanks to gravitational lensing, on the galaxies in the background behind the dark matter. We can see where the normal matter is because it's a normal matter. So we can tell that they got separated, and we can independently measure the gravity of the dark matter by itself, right? So no longer can you wonder, oh, maybe you just mismeasured the gravity, or it's a misunderstanding of how gravity works or something. We're able to tell that dark matter really is its own thing with its own gravity. And that really was a piece of very persuasive evidence that dark matter is a thing. Okay, but what is dark matter, right? What is it? We don't know. We have no idea. One popular theory is, well, maybe it's another kind of particle, right? Everything we've known so far is made out of particles, so maybe dark matter is also made out of particles. Sure. One theory is that it's made out of one particle. It's called the weakly interacting massive particle, WIMP, or WIMP, right? So maybe they're all from Columbus, right? And look at you, Ohio State. Yeah, I'm looking at you. So we don't know, right? But maybe dark matter is made out of lots of particles, right? It could have complicated interactions just like we do. There could be dark physics. There could be dark chemistry. There could be dark biology, right? There could be dark people, for all we know, right? Somewhere out there could be a dark physicist giving a lecture about the universe and saying, we understand 95% of the universe except for this little weird slice of stuff, right? That's us, right? That's us. We are the unusual slice of the universe. And remember, dark matter's not out there in the universe. It's here with us, the same way neutrinos are, right? There's dark matter in this room right now. You can't grab it or catch it because you can't interact with it, right? It flows right through us and ignores us, but it's here with us, and there's more of it than there is of our kind of matter, okay? So 5% of the universe stuff we know, 27% of the universe dark matter, right? That only brings us up to a third of the universe. So if you want to talk about what's the universe made out of, you at least have to get up to half before you say you've answered the question, right? So what's the rest of the universe made out of? What's this mysterious 2/3 of the universe? Well, it's something we call dark energy, right? But dark energy is just science code for we have no clue, right? Really. And don't be confused, the word dark and dark energy has no relationship to dark matter. It's just literally the word dark, okay? So you don't even get any clues from dark matter about what dark energy is. So how can we possibly know that 2/3 of the universe is this mysterious thing we don't know anything about? Well, it came from people trying to understand the history and the future of the universe. So brief recap of the history of the universe so far, right? Universe began with a big bang, right? Stuff exploded, right? Flies out from the beginning. And then people asked, what's going to happen next? Is there enough stuff and enough gravity from that stuff to slow everything down and stop it from expanding, turn it around and come back into a big crunch, right? That's option A for future of the universe, right? The big crunch. Option B is that there's not enough stuff in the universe and not enough gravity, and things will eventually slow down, but they'll never enough to stop, right? It'll just keep slowing down forever and gradually spreading out and cooling down into something known as the heat death of the universe, right? That sounds cozy. So your options are the big crunch or the heat death. So people said, well, let's figure this out. This seems important. So they went out there and they found out clever ways to figure this out, and they looked at whether the universe was expanding more slowly or more quickly a long time ago and this kind of stuff. And so they asked the universe this question, right? And the universe came back with secret option C, okay? It said, neither of your ideas are what's actually happening, okay? What's actually happening is that after the Big Bang, stuff didn't slow down at all, right? In fact, it's speeding up. It's accelerating. Things are moving away from each other faster now than they were 1 billion years ago. Wow, that's incredible. Like, how could that possibly be happening? If you know any physics at all, you know that to accelerate a galaxy, right, we're talking about hundreds of billions of massive stars, to push these apart faster and faster, that's acceleration. That requires force. That requires energy, right? That's why we're talking about 2/3 of the energy budget of the universe, because it takes a lot of energy to rip the universe apart, right? So, dark energy describes our knowledge of the fact that the universe is being torn apart. Galaxies are getting pushed away from each other faster and faster every single year. Something is creating new space between us and these other galaxies. What is it? We don't know. Why is it doing it? We don't know. Is it going to continue to do it, or is it going to stop? We don't know, right? We know that it turned on about 5 billion years ago to start creating this new space between us and other galaxies, but we don't know if it's going to keep doing that or not, right? So it's difficult to predict the future if you have no understanding of what the most powerful force in the universe is, right? But it's fascinating because the space between us and other galaxies is being created faster than light can go through that space. Okay? It's like Usain Bolt is running at you really fast, and somebody's laying new track in front of him faster than he can run, right? He'll never get to you. That's the same story for these photons that are leaving those galaxies now. They will never get to us. What does that mean practically? It means that things that are in the sky now, in the future, will disappear. They'll go out past the edge of our observable horizon, right? The sky gets darker and darker and darker every year, right? And we don't know what dark energy will do, right? We don't know what dark energy, what will happen. But it could be, if dark energy is powerful enough, it could even rip the Milky Way apart, right? And stars in our own galaxy could disappear, right? In 10 billion years, it's totally possible that you look up at the night sky and it's almost totally black, right? Making astronomy almost impossible, right? Personally, I'm skeptical that science will survive even the next 4 years of this administration, but if we are doing astronomy in 10 billion years, I wonder what it'd be like to be those astronomers, right? And have no clue what they're missing in the night sky. And you might think, well, I'm glad we live now, right? Well, we have the night sky to give us all this wonderful information about the universe. Remember, we're 14 billion years into the history of the universe already, right? What was in the night sky 10 billion years ago that's now gone forever? We have no idea, and we probably never will, right? Okay, so brief summary of our knowledge of the universe. Most of the universe is something we only recently learned we don't understand anything about, okay? So don't let anybody tell you that we've mostly figured things out. We only recently discovered how clueless we are, right? A huge chunk of the universe is dark matter, right? A mysterious thing. All we know about it is that it's a kind of matter. It's out there. We don't know what it's made out of, okay? The rest of the universe is me and you and dark chocolate, and we are the et cetera, right? We are the unrepresentative fraction in the universe. So in the beginning, I was telling you about all the amazing progress we've made in understanding how matter is put together and the up quarks and the down quarks. That story applies to a tiny little fraction of the universe. Can we generalize from that to the rest of the universe? That seems dangerous to me, right? Imagine you were studying an elephant's tail, right? You want to understand elephants, and you focus on just its tail for like 300 years, okay? And finally, somebody walks you around to the front of the elephant, and they're like, maybe you should look at the rest of the elephant before you draw conclusions, right? Now, if you're a physicist and you spend 300 years looking at the tail, your approach is going to say, well, maybe I can understand the rest of the elephant is like a linear combination of tails or like a perturbation on my tail theory or something, right? You're going to try to extrapolate from what you know into what you don't know. And you might think, that's stupid. Come on, nobody would ever be that dumb, right? Well, 10 minutes ago I said, what is dark matter? Well, maybe it's a particle, just like the other particles, right? It's exactly the same argument, right? We have no idea what dark matter is. It could be particles. It could be something else totally crazy, right? It could be a crazy new idea that totally blows our mind, a new kind of matter, not made out of particles at all, right? We have no idea what's out there, and we need to be careful not to overgeneralize from what we do know. In fact, I think this represents an exciting moment in science when we realize that we know very little, and we can sweep away everything we thought we knew and prepare ourselves for mind-blowing new ideas, right? So that's the point of our book. And it's not that we're doing nothing about it, right? Scientists are doing everything we can to understand these things. We have incredible space telescopes to peer deep, deep into the history of the universe and understand what happened in the early moments, which are very revealing. We have gravitational wave detectors to tell us about new ways to look at the universe. We have particle physics experiments to rip things apart. It's a pretty exciting time in physics, right? I hope we figured this stuff out before the aliens come and just tell us the answers, right? That would be disappointing. And I like to think that maybe this is even an era which will redefine our knowledge of the universe, right? That in 100 years or in 200 years, physicists will look back and say, wow, I wish I had been alive in 2017 or 2018 when they figured all this stuff out. What an exciting time to be a scientist, right? Or, you know, in 3,000 years, or even probably just 1,000 years, children's books will contain incredible basic facts about the universe that we don't know anything about, right? And those kids will look back at 2017 and say, what was it like to not know anything about the universe? The way you think about like a caveman or a cavewoman looking up at the night sky and not even knowing what stars are, right? What was it like to be so ignorant about basic facts about the universe? That's us, right? We are still totally ignorant about basic questions about the universe. So that's what our book is about. And in the book, today we talked about this one question, what is the universe made out of? Very reasonable question to ask. But there are other really basic questions about the universe we don't even really know how to tackle. Questions like, what is space? And if you're thinking, well, space is just emptiness, right? It's nothing. It's not a hard question. Yeah, but space can do things that emptiness can't. Like space can expand, right? The space between galaxies is increasing, right? They're not moving through space. New space is being made. Space can bend. That's what gravity is, right? Space can even ripple, okay? That's what gravitational waves are. So you can't just say, oh, space is not important. It's a thing. It has properties, probably properties we don't understand. It's like, imagine fish scientists swimming around in water for 1,000 years and saying, water, why is that important, right? It's easy, right? That's where we are with space. It's this physical thing we're in. It might even have an edge, right? We don't know. So all sorts of really basic questions that we haven't answered. So it's not that I want to tell you that science hasn't understood anything. We've made incredible achievements. But to me, science is more about asking questions and learning than about knowing things. And so that's the point of our book. So thank you very much for your attention.